Test. Test. Okay. Good. Well, I guess as only few people will attend the evening class. Well, I still wait for a while. I will start the class at 6:30. Well, this is recorded video. Later, the video will be uploaded to the channel. So those people who did not attend, you still can watch it. Because next Tuesday is the Chinese New Year, so I won't be able to give the lecture on Tuesday. So in that case, yeah, so tonight I will try to give an hour lecture to cover next Tuesday lecture. So in this 1 hour lecture, I will cover, I will finish the time complexity, just the last few slides of this analysis of algorithm, which I supposed to cover in today morning lecture. Yeah, and then after that I will follow up the stack and cube and some advanced advanced linked list or some variation of linked list. That I will, in the next 1 hour lecture I will cover variation of linked list, including the stack and cube. And next Friday I will cover an application of using stack data structure. So roughly that is the plan. After this 1 hour lecture, I will go to the Zoom meeting to talk about the this week lab, to give you an quick overview the lab question. Yeah, so that I received some feedback. So I trying to give some go through the lab 1 question, the lab section question in the Zoom meeting. Yeah, that particular video will be uploaded to the NTU Learn later. Okay, so if you have any question, you can post it in the chat. Yeah. Okay, a few more people joining in. Maybe we wait for a while. Can we find this lecture afterward on your channel? Yes, yes, yes. Yeah, it's just like as usual. After my live streaming video, you always can find all the past. Yeah, almost I would say instantly they will upload it into to the channel, so can easily find out. But for later the Zoom meeting about the lab section 1, normally it will take 1 or 2 hours. Then I will get the link for the video. Then that one probably will upload later. Maybe tonight if I can't get it, probably tomorrow I will upload it. Yeah, that one will upload into NTU Learn. NTU Learn. The lab 1 question go. Yeah, I try not to publish that lab question video to the public. Yeah, for the lecture, this one I think is okay. these are some general stuff, so I think should not be an issue. Okay, 6:30. Let us start this makeup lecture for next Tuesday. So this is where we stop in today morning lecture. So in the last lecture, I have discussed about this time complexity of sequential search. We have learned about the asymptotic notation. So in this example, you can see that there are several cases. It's not always you have a same time complexity. So first, in the previous lecture, I do consider first I try to consider that the search key is always in the list. So in that particular scenario, you expect there are three scenarios. The three scenario I need to consider: the best case, worst case, and on average case. So best case, not surprising that that will be always if the search key is the first nodes. If the search key is the first nodes, that is the best. Then you almost can instantly find out and return. Then this algorithm, the sequential search found the nodes and return. So it will take constant time to finish the search. In that particular best case scenario, I can conclude that in the best, if I assume the search key is always in the list, and in the best case scenario, the time complexity of sequential search in the best case scenario, is big theta 1, is a constant time. So if the search key is always in the list, then you expect that the worst case, I need to run in linear times, that which is the last nodes. The search key is at the last nodes. In that case, you first need to do this primitive operation to assign the head pointer to this PT, and then start running this loop for n-1 iteration. Because the last one, when you reach, you found that they are not, they are equal, then you stop. In the last iteration, before you execute the very last one, you reach here, you find that it's n-1 iteration. So in that case, the overall, the time complexity is you need to run n-1 iteration times 2 C2 plus always you need to run the C1. So overall, like I mentioned, that actually we don't really bother so much about the time, the constant time, the operation. We concerned about the problem size. How does the problem size affect my time complexity? So you can notice we also don't when we talk about the time complexity, we also not bother so much about whether it's n-1 or n-2. What we concern is on the linear. It is a linear function. So the time complexity in the worst case scenario is big theta n. And then on the average case, so I need to consider all the possible case. So all the possible case, that means it can be, the search key can be in the first node, the search key can be in the second node, the search key can be in the third node, fourth node, and all the possible case I need to consider. And in that scenario, in that case, that means actually, it can be in the first, second, or third, as I mentioned. Then it's quite fair to make this assumption that every item in the list have equal probability, have equal chance as a search key. This is the assumption I make. It may be true, it may be not true, but here I make this assumption. Otherwise, I cannot carry on my analysis. And in my view, it makes sense. Every nodes have equal chance. There's no any special reason that any nodes have. In this particular simple question, I didn't put any things additionally, so I think that is fair to set so. So in that case, I can make this assumption, and then that means the first nodes take C1. If the search key is at the first node, then the time complexity is C1. If it's at the second node, then it's C1 plus 1 iteration plus C2. If it's in the third node, it can be in the third node, so it's C1 plus 2 C2, and so on and so forth. So if it's at the last node, which is the worst case, is C1 plus n-1 C2. So each cases, there's a probability. They have an equal probability. You have n nodes, so the equal probability, that means their probability is 1 over n. All the cases have the same equal probability, which is 1 over n. Then you can just trying to rearrange it and trying to sum it up. So I think I've shown you. After you trying to do this, rearrange it, then it should be C1 plus C2 over n. This part is an arithmetic series. So you have n term. The first term is 0 based on the formula. The last term is n-1. So that's the summation for this part. Then you sum it up. Then you just further simplify. Then you will find that the time complexity on the average case, which is also n linear. So I also can conclude that this is a big theta n on average. So this is the assumption I've made earlier. The search key is always in the list. Then you definitely will ask, how about when the search key is not in the list? That means it's not a variable. In that case, you expect that if the search key is not in the list, then the time complexity will also, because this one you will run one more iteration, then will be n iteration. So it will be C1 plus n times C2. Anyway, whether you run additional one more iteration, it won't affect the result. In the end, it's still big theta n. So when the search key is not in the list, the time complexity is big theta n. So on average, I have to emphasize on average, the time complexity of sequential search, in the list or not in the list, is always linear function. So I can conclude that on average, the time complexity is big theta n. But if today I didn't mention the average case, it's general. I just want to know, that is normally we won't ask people, so details. We just simply want to know this algorithm. What is the time complexity of this algorithm? And you usually will see that online, normally they will tell you that the time complexity will be big O n. Because you need to remember that the best case is constant time. You cannot set big theta. The definition is not correct. Based on the definition, this statement is not correct. So probably when you didn't specify particular scenario, you will find that different scenario, and moreover different scenario, the time complexity can be different from constant time to linear or whatever. So in that particular situation, you probably very difficult to use the big theta notation to represent the time complexity. The best representation, the best notation you can choose probably is big O. And there are some scenario, sometimes due to some reason, you won't be able to know what is the worst case. Some algorithm, the worst case is too complicated. You have no idea. But you find that particular algorithm, at least you need to take linear times to execute. And in that situation, we may use the big omega to represent the time complexity of the algorithm, which is not that common. You'll find that online, usually they like to use big O to represent the time complexity because you usually would like to know the worst case scenario. What is the worst case scenario? Probably from here, if I tell you that this particular algorithm, the time complexity is big O n, you will know that the worst case scenario is in linear. If today, for example, this time complexity of sequential search, actually I also can set that it is big omega 1. The time complexity of sequential search is big omega 1. This statement is correct, but it's not clear. Because I only tell you that it's big omega 1. How bad it can be, you have no idea. But if I tell you it's a big O n, at least you know that the worst case definitely is up to linear. It won't worse than linear. So at that case, you can decide whether you want to use this algorithm or not. And you'll find that quite difficult. If you want to general talk about the algorithm, usually we very difficult to use big theta because it's a tighter bound. Unless it's very certain the algorithm always is linear, then you can use this big theta. Or you are only discuss about particular scenario. In that case, the time complexity is quite certain. It's definitely type bounded in that particular class. In that situation, you can use the big theta. So it depends the problem. And then you should choose the most appropriate notation to represent your time complexity. And when we talk about the time complexity, you will find that we only talk interest about the order of growth. They are under which category, which class. Okay. So of course, yeah, all this asymptotic notation, we can trying to do some simplification. Yeah, if you multiply any constant, yeah, gn. Yeah, you also, if fn is in all big O cgn for some constant c greater than 0, then of course I can set fn is in ogn. Yeah. So if fn is in ogn, gn is in ohn, big ohn, so it's also implied that fn is in big ohn. Makes sense, right? So if this is a linear, let's say gn is n squared, hn is n cubed. So of course, if fn is in O n squared, n squared is in O n cubed. Not surprising that you can conclude that n is in O n cubed. Yeah, correct. So you sometimes you can use this to simplify your notation, okay? Your representation. Then yeah, this example. So I also can, yeah, if f1n is in OG1n, f2n is in OG2n. In this scenario, f1n plus f2n will be the maximum g1n and g2n. What does this thing mean? Let's say if I have an algorithm, let's say I have an algorithm. Yeah, there are two parts. The first part, it take f1n to execute. In my second part, it take the f2n to execute. Yeah. So when I trying to consider the overall, the whole algorithm, what is the time complexity of the whole algorithm? Yes, you're trying to sum it up, f1 plus f2. But when you write in the why you take the maximum, just give you an example, probably will be clearer. Let's say f1, the first one, is somehow run n iteration. Then the f2, this part, they're trying to, is some algorithm running in n squared. Yeah, running in n squared. Then of course we are more interested about the maximum, the worst one, the worst portion, because whether you add another few more constant here and there or some linear, yeah, this portion take most of the computational times. So not surprising, this one is in ON, this one is in ON squared. So overall is still ON squared. So that is, you choose the maximum. Yeah, same thing, 5n plus 3 log 2n. Then the linear, the time complexity, the order of growth is the highest compared to the logarithmic. So in the end, you can conclude that it's big ON. Another one, if f1n is equal to OG1n, f2n is equal to OG2n, then in that case, it's like a nested algorithm. That is different. It should be the other way. You have an algorithm. Yeah. This one, maybe there's a for loop or something like that. Inside this, there's another part, which is f2 part. Then outside the one, they use f1. They need the time complexity. If you not consider this portion, yeah, the outer loop, yeah, you need to run f1. Inner loop is f2. So when you f1 times f2, so in that case it's f1 times f2. The time complexity is g1 times g2. For example, if the inner loop, it take a logarithmic log 2n. Then outer loop is n square. So it's, let's say, 3n squared in this example. So overall should be 3n squared times log 2n. Then the time complexity is n squared log 2n. You only can, omit this. N squared times log 2n is the overall, the time complexity of the whole algorithm. Okay, so other property of asymptotic notation sometimes you can use to simplify your time complexity representation. Reflexive. Fn of course is in all Fn. Fn of course is in big omega Fn. Itself. Fn, because Fn definitely is in big theta Fn. Transitive also, if that's what you see just now, Fn is equal to OGN, Gn is in OHN, so Fn definitely is in OHN. This not only apply on big O notation, it's also apply on big omega and big theta. Maybe big omega, give you an example. If this one is maybe the other way around, Fn is n cubed, so n cubed definitely is in big omega n square. Then n square is in big omega n. In that case, I can conclude that n cubed is in big omega n, based on the transitive of omega. Then symmetric only apply on big theta. If Fn is in big theta Gn, then you only can set Gn is also, you only can conclude that, implied that Gn is in big theta Fn. It only work on big theta. So this you need to take note, symmetric only work on big theta. Okay, so give you some, I think someone in the morning have asked about this question. Constant, as long as you can instantly find, just like you access the midpoint of an array, that you can instantly achieve it. That is under the constant class, the complexity class. For the logarithmic class, you will learn about binary search. In that one is the logarithmic class. Linear, like just now the sequential search, or we also call it as a linear search, is a kind of a brute force approach. You try out, you search every component, you read every item. This definitely is a linear search. Definitely is linear function. The order of growth is in n. Then in the next level, you will learn about the sorting. In sorting, there's a sort algorithm, merge sort, which is the linear logarithmic. And then there's another one we will introduce you in 2000 module, is an insertion sort. You will find that this one not so good, which is a quadratic class. They will take n square. The time complexity will take n square. Metric inversion is in qubit. So normally when we do this metric inversion, it's very time consuming. Because the complexity is in qubit. And you may heard about Tower of Hanoi, which is exponential. Let me see. Get it. That is the Tower of Hanoi. The Tower of Hanoi, basically you have n plate. You're trying to move the plate from this tower. Your target is from move the end plate. Here I give you 3 plate. It can be n. You're trying to move this end plate from here to here. That is your target. So, but there's some rule. Tower Hanoi, each time you only can move 1 plate to one of the tower, here or here. Then and each time you move, you need to make sure that the bigger plate cannot be on top of the smaller plate. So in this case, yeah, you have to move this one to here. And this one you can move to here because it's smaller. Yeah, so you only can move in this way. Probably I move in the wrong state. I have to move this one here, and then this one here. Am I right? No. Okay, I made a mistake. First, I should move this one. I move this one. Then I move this one. Then I move this one. After that, I move this one. Then I move this one. Then last, I move this one. So you will be in the target tower. So that is the Tower of Hanoi. 3 plate, 7 step, not too difficult. But when you go to n step, you will find that the time complexity is 2 power to n. If you know the answer how to do the Tower of Hanoi, you will find out that this particular Tower of Hanoi, they have 2 recursive call. They do the 2 recursive call. I'm not surprising that. And every time your recursive call only reduce the plate by 1. So in the end, you will find that the complexity is in exponential. And then another one is the traveling salesman problem, which is n factorial. Because basically they need to traveling salesman problem is like originally it's like US have 50 state. Okay, here I just give you an example for 5 city. You want to find the shorter path to visit every city once, and in the end, you need to go back to the initial state, city, the first city you visit. So you need to find the shorter path because you can from city 1 to city 2. You also can from city 1 to city 3. You also can from city 1 to city 4 first. And you also can go to city 5. Yeah, so city 2 also can be moved to city 3, city 1, city 3, city 4. Yeah, city 3 also can go to city 4, city 5. Yeah, that means all the city can visit each other. There's a different distance. You are looking for a road, a path to visit all the city. And when you reach the last city, you will go back to the first city. So not surprising, to find out the answer, you need to try out all the combination. So the time complexity of this problem is n factorial. Yeah, so these are the few the time complexity of some example for different class: constant, logarithmic, linear, and quadratic, cubic, exponential class, and factorial class. So when time complexity of algorithm A grow faster than algorithm B for the same problem, then we can say that the algorithm A is inferior to algorithm B. Because the time complexity A grow faster. When I said A, the time complexity A grow faster than algorithm B. That means A is slower. The computational time, it will take longer time to finish, to complete, because the growth rate is faster. Yeah, so I think in the morning, there's another student have asked the same question. Yeah, so that need to take notes. When you have a time complexity, the order of growth is faster, like n factorial, 2 power to n. They grow faster than linear ramic. Then yeah, you expect that, of course, this kind of algorithm is your preference. Then having, normally we try not to have this in the earlier morning lecture I've shown you. If you have 2 power to n algorithm, the time complexity is 2 power to n. You expect that your n just need to increase a little bit. The computational times will grow into a very scary number. It can be take years to complete a very simple, a small problem size. Just need some small number. For example, you can try to implement the Fibonacci number. Yeah, you trying to write the factorial. I have mentioned that one is exponential also. You just need to substitute n equal to 100 or maybe 100 or 200. You will find that you will take a long time to run and get the result out if you use the recursive approach to implement the Fibonacci number. Yeah, so that is explained why normally we're looking for better and lower growth rate algorithm to solve the problem. You also will learn this when you compare the merge sorts and insertion sorts. Yeah, you can see the difference, the time complexity. Okay, so these are the time complexity. Yeah, here I didn't mention about the space complexity, but the idea will be the similar to the time complexity. So basically, instead of calculate the number of primitive operation, space complexity is trying to determine the number of memory, the usage in this particular algorithm. So for example, it's like you normally will look for, normally it can just simply look at the top of your declaration. You use how many integer, float, character to array, and then you declare how many linked lists. In your linked list, yeah, or how many, later you will learn about binary tree. Yeah, so they just trying to count the memory usage and trying to also can be trying to represent them in big O notation and big theta notation or big omega notation. So all the similar thing you can apply. It's just like the object you count is memory instead of time for the space complexity. For example, you trying to yeah, if you have if your algorithm only use an integer, an array of n integer, so the space complexity is big theta n. Again, we don't really bother so much is an integer or floating number or double or character. We concern is like the problem size is n. So if a metric is used to store the edge information of the graph, so probably is like, yeah, it's depend on your edge. Let's say my edge is n. In that case, this particular metric will probably be in n squared. Yeah, this will, when you cover the graph, you will understand why it is so. But yeah, just in short, if you declare a metric, n by n metric, of course, the space complexity is big theta n squared. Then, and later you will see some algorithm. When we want to improve the time complexity, sometimes when we go to, later you learn about the hash table, you will find that sequential search, you only execute, you only can, the time complexity of sequential search is linear. And then later you learn about binary search. Yeah, you can improve. After I sort out the data, I can improve my time complexity from linear to logarithmic. And if you want to further improve from logarithmic, the search time, to improve from logarithmic to constant time, and you will find that if you just simply improve the algorithm, it's not that easy. You need to do this kind of space-time trade-off principle. That means I have to sacrifice the space. I'm trying to use more space. I'm trying to use more memory to store the data, to store the information, so that I can improve my time complexity. So that means you will find that that kind of algorithm, usually the space complexity probably will get worse, but the time complexity will get better. It's a kind of a trade-off. If you usually that it will be the case, because you find that you have a lot of memory space, your RAM, your storage is sufficient for you to store such a big data. Then but it can, by doing that, you can improve your time complexity. You will choose to do so. But sometimes for those application in embedded system, maybe, yeah, they are the other way around, because the memory, the storage is limited. You have very little memory. Then a lot of time, we, instead of choose a powerful good algorithm but computational expensive algorithm, we will choose some not so good algorithm, but you don't need such a big your probably your time complexity will be not so good, but your space complexity can help you to save a lot of memory because you have limited resource. Yeah, so this kind of a trade-off is depend on your application. Where are you going to apply your algorithm onto what kind of a system? Then you will choose appropriate algorithm. Then this is a kind of a space-time trade-off you will encounter later. Yeah. So this is the analysis of algorithm. Okay. So yeah. Discuss. Next, I'm going to go into quickly go through. Where is my? Okay. Something. Okay. So next, I'm going to give the lecture for. Actually, it's for cover the next week Tuesday lecture. Tonight, I only cover the advanced linked list, stack and cube. On next Friday, the lecture, we will cover the algebra expression conversion, yeah, which is one of the application by using the stack. So in this lecture, I will just simply go through the data structure, advanced linked list, some variation of linked list, and stack and cube. So quickly summarize what you have learned in 2 weeks ago, last week, last week. So in the first week, you have learned about, you need to make sure, I think later I will talk about the lab 1. Make sure you really know how to use the dynamic memory management, memory allocation, to use the malloc to do the dynamic memory allocation. And then how to use the free function to deallocate the memory block you create by malloc. And also you need to know the linked list, because subsequent data structure we discussed, we all use the linked list as the basic structure. Yeah. So this linked list, this is a self-referential data structure. So you can see that I declare a list nodes. Inside this list nodes data type, there's a list nodes pointer. So this is a self-referential structure. Then they form the basic element of a linked list. So you can use this to create a nodes, and each node will use the pointer here to link to the next nodes, so that you can form a linked list. And we also introduce you how to print the list, the linked list, how to find nodes at particular index, and how the key is how to insert a nodes, how to remove a nodes. These have been covered in last week lecture. And then we also briefly compare the linked list and array with you. So you will find that, yeah, to display, of course, whether you are using linked list or you are using array, you want to display or print out all the nodes, all the element in an array or a linked list. You have no other shortcut. You have to run a while loop and print out each of them. So in that case, display, yeah, by using linked list or an array, they are the same. Search, probably array will be performed a little bit better than linked list, because linked list, you want to search the nodes, you want to go to particular index to retrieve the data. Usually you have to run a while loop, especially simply linked list, which we covered last week. You have to travel all the way to that particular location and then you can retrieve the information. But array is random, is the strength of the array is random access. You just give me the index, I can directly jump to that location and retrieve the data almost in constant time. So that probably is the good thing for array. The strength of a linked list is they are very good in insertion and deletion. That means you can expand your linked list or string your linked list or rearrange your linked list easily. But array is not good in this operation. Yeah, you can see that you want to insert a node compared to insert a node in array, or want to add additional element into an array. It's almost impossible. You only have one way to do it, is that you have to create another array and copy the old element from one array to another new array. So that definitely very time consuming. Yeah, check the size. Array at the beginning already know the size, but the size is fixed. But for linked list, you want to check the size. Yeah, we have, yeah, if you use the initial definition we use, probably you will need to run the while loop. But this can be overcome. I have introduced to you. If I introduce another structure, which with a member, and this member can help me to keep the size of the linked list, the length of the linked list, then that means every time if I would like to know the size, then I just simply return this particular member. And every time if I insert a node or remove a node, I will increase or decrease this particular member. Then I don't have to do any extra work on it. I can easily retrieve the size of the linked list easily. That can help me to improve the time complexity to search the size of a linked list by introduce just a variable. Yeah, this also explained just now the time space trade-off. So I just need to use one extra memory unit, one integer, but my time complexity can be improved from linear, this while loop, they take linear times, to constant time. So that is yeah, a good choice to do so, worth to do it, because space wise, the space complexity, I only introduce one memory unit, just an integer, is constant time. But my time complexity can be improved from linear to constant. My time complexity improved in this function. So it's quite good to do so. Yeah. Just remember to modify your code, your insertion and remove, because this step also won't cost you a lot. It's just cost you a constant time. Every time you insert the nodes, you need to spend so much time complexity to do so. And then you just, in the end, you just simply increase the size by 1 or decrease the size by 1. That is a constant time. So overall, this is something worth to do it. So we have introduced you all this, yeah, the different prototype. on how to use the linked list. And I think I also share to you the difference in the 5 nodes. The 5 nodes using the list nodes pointer or use the new structure linked list. The different, actually the algorithm, they are exactly the same. Just like you're using the data different structure definition, the something a little bit different, but the overall the algorithm are exactly the same. After you introduce this, you will become this. So in this section, I just briefly I just share some in fact the linked list, there are a lot of variation, just like our COVID-19. There are a lot of variation of the linked list. Here I introduce a few: doubly linked list and circular linked list. In fact, the tutorial one I already show you the circular linked list, and then the circular doubly linked list. And stack and cube, you can think that is a special case, some special case or some linked list with some special property. So that is what we will cover in the short while. Application wise, we will discuss next week. So here I only introduce you 3 variation of the linked list. Okay, you have learned about the singly linked list. In the singly linked list, you only have one link, which is bring you to the next nodes. Then you should realize that there's a problem. Your way is one way. You only can if you want to visit, you're only able to visit the next nodes. And for when you want to insert a node, or sometimes you want to know where is the previous nodes, for singly linked list, it's very troublesome to know where is the previous nodes. You can see in the insertion, the nodes insertion or the remove nodes you did in your lab. Having one link sometimes is not very convenient. So in fact, you can easily create a doubly linked list. Just introduce another pointer which point to the previous nodes. In that case, your linked list can move in 2 directions. You can move forward, you also can move backward. That can help you to give you more flexibility to visit the nodes, the previous nodes or the next nodes easily. But of course, your implementation, you need to do a little bit more, a few extra work to do, because for example, the first nodes, there's no previous nodes. So in that case, the previous nodes will be assigned to null pointer for the first nodes. The last nodes, just like the singly linked list, does not have the next nodes. So the next nodes, probably you will assign a null pointer. The rest, every nodes always have the next nodes and the previous nodes. You always need to assign the appropriate pointer to point to it accordingly. So for example, I think for search, display, search, check the sites is very similar to the singly linked list. Something you need to do a little bit special is on the insertion. When you're trying to do the insertion, let's say I have this doubly linked list. Of course, first I need to know where is the location I want to put. First I will declare a new node which I'm going to insert, and then I need to locate where is this current node. After I know where is the current node, then for the doubly linked list, I don't really need to know where is the previous node, because from the current nodes I can easily find out where is the previous nodes. So after that, probably I can, once I have reached these 2 points, I can easily update my new nodes. Next, just simply point to the current nodes, and then the new nodes previous link, the previous nodes link will point to, can easily find out the current pre, from the current pre to find out these nodes. and then update it accordingly. Once you update these two links, you will notice that actually this doubly linked list already not ready. This one not yet. So next step, I already can update these nodes. The next nodes point to here. Okay, I think I point to here. Yeah, these two I can update it. In fact, in any order, I think should be fine. Whether it's this one or this one, because you notice, okay. That's why I said that the solution is not unique. There's a lot of way. Yeah, the order, I think this one and this one can be swapped. It's still working. Yeah. In short, you just need to update this one. So probably I can update this one first. Then next, I update this one. And then update this one. In my example, I update this 4 in this order. But it's not a unique solution. Because you find that doubly linked list, they give you a lot of flexibility. Yeah, you can easily to know where is the previous nodes, next nodes. The key, whether it's a singly linked list or doubly linked list, the insertion or delete, one principle is that you try not to lose the nodes. You still need to use it. Yeah. So you need to make sure that there are someone point to it. You're able to find it back. Yeah, when you're trying to rearrange the link, yeah, this is something you need to take notes. Yeah. So this is the doubly linked list. You can go and try to play around with it to see whether you're able to implement a doubly linked list. Yeah, here just give you a rough guide. You can go and try it out. Another one I also have introduced you in the tutorial question. Yeah, actually you find that if it's normal singly linked list or doubly linked list, the last node is point to the null pointer. But what happens if I change it? Here in this example, the circular linked list, I try to change it. The last nodes, instead of point to the null pointer, I let the last node, the link of the last node, instead of point to the null, I try to let it point to the first node. In that case, you will find that it will form a circular linked list. That means you will look back to the first node. First node go to the second node, third node, fourth node to the last node. Last node, the link will bring it back to the first node, so that you can keep looping in the linked list, this circular linked list. Yeah. So this in some application is very useful. For example, you have a few tasks, you want to repeatedly do these few tasks, you can create a circular linked list to let to keep traveling along this circular linked list to do different tasks in different nodes. When you reach the last nodes, you automatically loop back to the first node, repeat the procedure again and again and again. But sometimes you need to take notes that when to stop, because this circular linked list, if you don't have any criteria, they will just keep looping. You won't be able to encounter any null pointer. Yeah, you can just keep looping forever. Similarly for the doubly linked list, yeah, that's when this is the combination of these two variation we mentioned earlier. The last nodes next will point to the first node. Then the first node's pre will point to the last node. So that will form a doubly linked list. Of course, this one you expect they have more flexibility. You can move forward, backward. Can easily move along the linked list. This circular doubly linked list. Then you can go and think about it, how to insert a node, remove a node. It's very similar to the singly linked list. Okay, so for circular linked list, basically display the search site. The last node, just need to take notes that the last node link is equal to the head, not the null pointer. So you probably need to have either the sites first, you have some linked list member which can provide you the sites. Then you can instead of looking for your stop criteria, your while loop stop criteria, instead of looking for null pointer, you can make a counter to count. You only read, yeah, this number of, you only run the iteration based on the size of the linked list to decide the iteration you need to run. So you will stop when you reach the last node. And then insertion and delete, I think there's no any special case, because whether you insert in the first nodes or insert in the last nodes or insert in the middle, yeah, always there's a previous nodes. Even the first nodes, after you introduce this circular linked list, circular link from the last node to the first nodes, the first nodes, the previous nodes of the first nodes is the last nodes. So insertion, you find that you can, insertion and deletion, you find that you can simplify compared to the singly linked list. Okay, so these are very there are a lot more. All these linked lists we introduce, the variation of linked lists we introduce here are considered as a linear data structure. So after we cover the stack and cube, we were going to cover some non-linear data structure, which is tree structure. Yeah, so in fact, all of them are using the linked list. Just like we're trying to introduce a little bit different link, then to form different structure, then we can have more interesting data structure to help us to solve the problem. So next, I'm going to introduce another tool before I end today's lecture, stack and cube. Basically, stack and cube is just a concept. Sometimes I will consider this is not really a linked list or what particular data structure. It's just a concept only. So you, based on this particular concept, you can use the linked list or an array to design your data. Yeah, you can use the linked list. You just introduce this additional concept onto this linked list or array to have this kind of a characteristic to solve some problem. So what is the stack? It's just like in your daily life. Yeah, just like just now the Tower of Harmony. Yeah, this is considered a kind of a stack. I got a few plates. I just like trying to stack them one after another. So what is the property? One of the key of the stack, you will find that when you insert, you always insert at the top. When you remove, you only can remove at the top. So in that case, you will find that there's an important property is the last plate you enter, it will be always the last in. Sorry, this is the last one. So this is the last plate enter the stack, and you will find that it always will be the first one removed from the stack, and the one first in at the bottom, it always will be the last one removed from the stack. So the stack is also known as a last in first out data structure, or first in last out data structure. And yeah, that's why I said it's just a concept. In short, stack is just like last in first out or first in last out data structure. That's it. Yeah, whether you implement it in linked list or an array, is depend your application. Yeah, that is an implementation problem. But the concept you need to know, stack is just last in first out or first in last out, and the nodes insertion or remove always at the top only. That, in other words, you theoretically you are not allowed to touch the second or third. You only always can invoke is access, remove, or insert at the top. You are not allowed to access the information in the second nodes or third nodes or the last nodes in the stack data structure. So queue is just like in your daily life. You buy food, you queuing. You go to grocery, you go to buy something, you always need to make the payment, you always need to queue. So just like you're queuing, you always queue at the back and you make the payment at the front. So that's when this kind of a data structure, they insert at the back, at the tail, and remove at the head. So you will find that first in will be first out, last in or last in, last out. If you are the first one enter the queue, you definitely will be, theoretically, you're supposed to be the first one removed from the data structure. Left. So that is the first in, first out data structure. Same thing, you always can implement it in an array and linked list. But you'll find that stack and queue, linked list is a more appropriate data structure for linked list and for the stack and queue, because you always need to insert and remove the nodes from the data structure, stack and queue. So yeah, you have learned about this data structure, linked list. So these are the linked list structure. We introduced the sites, this linked list structure. We have learned about how to display, how to search, how to insert, how to delete. This we have learned before. So stack, I just need to reuse the linked list data structure. Simply rename it. Instead of call it linked list, I just simply give a new name called stack. Theoretically, as I mentioned earlier, you are not allowed to access the second or third. You always only can access the first nodes at the top. So in that case, probably you are not able to simply print out all the element in the stack. So this one I'm not considered, because you want to print out all the component, all the nodes in the stack. That means you have to remove all of them. Yeah, so that probably not appropriate function you should have in your implementation. But you can pick, you can push, which is insert, I call it push. Delete, I call it pop. Push and pop and pick probably is the best. The thing you can do, the 3 tasks you can do in the stack data structure. Sites, probably you only can check whether it's empty or not empty, because you cannot check, you cannot count. So probably you only simply check whether it is empty or not empty. As long as there's something inside, of course it is not empty. I think that is good enough for our application. And then queue is a little bit different. Later I will explain why I need to introduce another new pointer here, tail pointer. Yeah. So, but basically they are still same as the linked list nodes. Just I introduce one more additional pointer here. Yeah, here. Yeah, the head pointer. So I not only have head pointer, but I also have another new pointer called tail pointer. Later I will show you why I need to do so. And then same thing, queue, you're also not allowed to access other nodes. You only can insert the nodes at the tail and remove the nodes at the front. And you also only can retrieve the data, retrieve the nodes at the front. So you only can enqueue at the tail, at the back, and dequeue at the front, and observe what it is at the front. So that is the get front. So you only can do these 3 tasks. Probably you can't print out the queue. If you want to print out the queue, you have to remove every node in the queue. That may be not appropriate. Same thing, to check the sites, probably we only just need to check whether it is empty or not empty. I think it's good enough. So in short, stack function, just take notes in my definition. Pick is just inspect the item at the top of the stack without removing it. I'm not going to remove it. I only pick. I only look at it, what it is inside. Then retrieve the item. But I won't remove the item. That's called pick function. If I want to remove the function, I will use the pop function to pop it up and throw it away. And pop function won't go and inspect the item. You will just simply pop up the item and throw it away. And then push will just add the item into the stack. And then check whether it is empty. So just take note that in short, you always only can do something at the top. Other part, you cannot touch it. So that is the first in, last out data structure, stack structure. So quickly give you the the code I have. Pick the top. This one quite simple. I just need to check what is the first item. So my job just need to return the content in the first nodes. Depend, of course, in this example, my item is an integer. It can be any other things. Yeah. So okay, maybe I can explain this. Why we can't print list and print. You can print. Of course you can print list. Okay, that's why I said theoretically we try not to implement this print list in our stack structure. You're not supposed to access the second nodes, third nodes. You're not supposed to go and directly access the subsequent nodes immediately. You want to access the second nodes, you must remove the first nodes. Because in the stack data structure, you only allowed to access the nodes at the top. That is the rule set by the stack data structure. So if you want to print out this, you will breach the rule. But of course, if you implement it as a linked list, I'm not surprising that especially in C programming, you can print out the list. But please not to do so, because you will breach the rule of the stack data structure. So that's why I keep emphasizing theoretically you can't print the list of the stack or queue. So do you mean that conceptually we are only, yes, conceptually you only can touch at the front. For stack only, you only can always, you can see that whether it's the pick, push or pop, I only do it at the top only. So in other words, theoretically, conceptually, whatever, you have no idea the rest of them. You only know that at this moment, I only can inspect what it is at the top. But what is the second item? At this moment, I don't know. If I want to know the second item, I have to pop up the first item first. And then I can look at the second item. Yeah, so that is the important concept you need to know about the stack. The rest, I think the implementation is quite straight. So you pick, you just look at the first item, return. Yeah, depend is integer or double or float or whatever. Sometimes I maybe return the nodes, the whole nodes, if the data is very complicated. Depend on my application. So pick is quite easy. Just take notes that only simply return. I don't do anything further. For the pick, I only inspect the item only. For push, I'm trying to insert. In other words, you always insert at the front. So that means you can reuse the insertion nodes. The insertion nodes, which we cover in the linked list. But actually, yeah, that's when you're trying to insert at the index equal to 0. At the front, in short. So well, normally I prefer not to, because I don't want to memorize this function. Since it's insert at the front, so I just insert at the front accordingly. So you will find that actually this one is exactly same as this part, because I don't really need this part in stack data structure. So in my implementation, I only include this portion. It's good enough for stack data structure. So that is the push function I will use. Yeah, it's exactly same as the linked list you have learned earlier. You can compare malloc, put the item, then update the new nodes next link, update the new nodes next link. Then after that, update the head pointer, update the head pointer, update the head pointer. Yeah, increase the size, exactly the same. And you only can insert the nodes at the front for stack data structure. So similarly, which you have learned in lab 1 to remove nodes. So in port function, you also same thing, you only can remove the nodes at the front. Of course, you can call the remove nodes function, but I also prefer to implement that particular case is good enough. Just remove nodes at the front. Because you won't remove the nodes in the middle or at the back. You are not allowed to do so. So yeah, normally I will implement this port function in this way. Okay, and take note that port function, I don't care what it is. I just simply take the first nodes and throw it away, pop it up and throw it away. That is a port function. So if you want to know what is the content before you pop it up, please use the pick first. And then after you pick, you get the information you want, you pop it and throw it away. If you simply pop it, the return value I did is just checking whether you successfully pop up or not. That's mean I will, through the pop function, I will not be able to know what is the content inside. If you want to know what is the content in that pop-up nodes, the first nodes, then you need to call the pick function to pick it first. Okay, then okay, this one to check whether the stack is empty or not. That one very easy. You just check the size. If the size is 0, mean it is empty. If the size is not 0, of course it is not empty. Very straight. Okay, so this is the stack data structure. Yeah. So, and then similarly, we work on the queue will be in the same manner. So queue structure will introduce a tail pointer. The rest, you have head pointer in the linked list, in the stack, also a variable in the queue structure, because I need to dequeue it at the front and queue it at the back. Yeah, that explains why I need a tail pointer. You will see, based on my definition, get front will only same as a pick, only inspect the item at the front. In fact, I don't need to inspect the item at the back. When you insert the nodes, when you enqueue it, you add an item at the end of the queue. You definitely know that item, because that item is on your hand. You want to enqueue it at the back, you don't need to call. Before that, you should know. The thing you don't know probably is the one you're going to dequeue. The thing you're going to dequeue, the nodes you're going to dequeue, which is at the front. Yeah, so you will get front to get the information about the nodes you're going to dequeue. And then you dequeue it. Same thing, enqueue, dequeue will just simply insert the nodes and remove the nodes. One insert the nodes at the end, the other one remove the nodes at the front. So when they remove the nodes, dequeue will just simply dequeue it. That means they just take the nodes at the front and throw it away. They won't go and look at it. They will just throw it away. So they will free in the function, directly free it. So if before that, if you don't get front to check, then you have no chance to see it anymore. Then empty queue is empty queue. You just check whether it's empty or not empty, just like it's empty stack function in the stack data structure. So basically, user only can add a node from the back and remove a node at the front. So that is the first in, first out data structure. Yeah, later I will show you, after you introduce the tail pointer, what is the advantage. Probably you also know. So same thing, we get front, we inspect the first item. So just one line, exactly same as the pick function. Yeah, just simply check whether what is the first item. Okay. Yeah, exactly same as the stack data structure. So just simply return the item at the front. Then enqueue and push compare. Yeah, when you push, you insert the nodes at the front. So you decube, you're trying to insert the nodes at the end. But by doing so, you will find that there's a problem. That means every time you you encube a nodes into the cube structure, if you call the old function, you are in trouble. Every time, actually, that algorithm, the insert nodes, is trying to run a while loop to bring you all the way to the last nodes. Yeah. For push function, well, if you want to use the insert nodes, I think it's still okay because, yeah, your index is 0. Basically, they just insert the nodes at the front. So the time complexity, it won't affect. But this one, if you use the linked list function, you reuse the linked list function, you were in trouble. Initially, it's still okay. When your nodes, when your queue increase to 1 million, 10 million, you'll find that you will take times to encube a new nodes into this queue structure. So to make it more efficient, probably I need to rewrite the encube function. So therefore, I introduce the tail pointer. Introduce the tail pointer if I want. So the tail pointer will always point to the last nodes. So let's say now I want to encube a new node 40 into this queue structure. And then my tail pointer is point to the last nodes. So in that case, yeah, okay, I think I changed the order. So I should trying to just let the tail point. So first I create the nodes. This portion I create the nodes. So I create the nodes. And then okay, maybe I consider the general case first. So the Q pointer till next, this one will point to here. Will point to the new nodes. And then I will update the tail. I will let this tail point to the new nodes. Yeah, I let the tail point to the new nodes. And then I let the sides increase by 1. But I also need to consider a special case. When I encube the very first nodes, that means my queue is empty. If my queue is empty, which implies that the head pointer is point to a null pointer. Not surprising that the tail pointer is also a null pointer. A tail pointer is a null pointer. Of course, if you run this particular line, your program will crash because tail is a null pointer when you have an empty queue. So in that case, actually, you are, instead of assign the new nodes pointer, let the tail next point to the new nodes. You are trying to let the head point to the new nodes. That's mean initially you have a new empty new nodes, a new queue. So the new nodes actually is point to the head. Let the head point to the new nodes. And then same thing, these two lines are exactly the same. The tail will point to here. After that, then you increase the size by 1. That is the encube function. So that means every time you insert a new node, you will update your tail. You update your tail, you move your tail to the last node, the new last nodes. So every time you can find that the time complexity of this new encube function compared to insert nodes. Yeah, it looks like this insert nodes only one line. But inside this insert nodes function, there's a while loop. The time complexity is big theta n. But my new function, encube function, you can see if you look through, there's no while loop. Implied that the time complexity actually is a constant time. Every time you encube a new node, the computational times is always constant time. But this particular insert nodes given in the linked list function, yeah, the time complexity will be linear. You have more data, you have more nodes in the queue, you will take more times to enqueue the new nodes. Space wise, yeah, both of them take n data to build up the queue. So the space complexity, there's no difference. You introduce one pointer, yeah, it's nothing. Those space is negligible compared to the problem size. So that is the enqueue. Similarly to the dequeue function, you will find that is dequeue is remove the nodes at the front. Port function is remove the nodes at the front. So not surprising that these two functions will be about the same. Yeah, only this part, because you need to always consider the tail pointer. So there's a scenario when your head is a null pointer. That means you after you remove the last node, you dequeue the if you are the situation is like you only left one node, you dequeue it. After you dequeue it, you need to remember that you need to let your tail pointer also become a null pointer. Because when you're trying to free the the memory block, your tail pointer still point to the free memory block. Yeah, although that block already free, but your pointer still point to that memory location. So you need to remember to update your tail pointer after that. So that's why I need to introduce this if statement. When your head pointer is a null, that means you already removed the last nodes. Then you also need to let your tail become a null pointer. The rest exactly the same. You can see here I declare a 10 pointer. Here I declare a 10 pointer. Here I assign the head to the next. I assign the head to the head next. Then I free the 10 pointer. I free the 10 pointer. I reduce the size. I also reduce the size. For these two functions are exactly the same. Just need to consider the tail pointer and update it in certain in the special case. You only left one node and you dequeue it. Your tail pointer, you need to make it as a null pointer. So last one, the empty cube. Yeah, if it is empty, yeah, just check whether the size is equal to 0 or not. Both are exactly the same. Yeah, so this is the stack and cube. Okay, to summarize, yeah, okay, yeah, this stack is first in, last out data structure. Queue is first in, first out data structure. Actually, that's it. The rest, yeah, it's just the implementation. So in the stack, okay, in the stack, I have mainly these are the three key functions I can do on the stack data structure. I can push the data at the front. I can port the data. I can remove the nodes at the front. I can inspect the item at the front. Then for the queue structure, I can enqueue, dequeue, and get front. So when I enqueue, that means I can insert the nodes at the back, at the tail. And then I can dequeue, I can remove the nodes at the front, and I also can inspect the nodes at the front. These are three tasks. This is probably the only three basic tasks I can do on the queue data structure. So normally we only use these three functions to work with the queue data structure to solve the problem. For the stack, we also only use these three functions to play around with these three functions to solve the problem. Of course, like I said, in fact, it's on probably in some other language, actually they can block everything to prevent you to access other element. But for in the C programming, probably it's very hard for me to block you. Yeah, so that's why I keep saying it's theoretically you are not allowed to print stack or print cube theoretically. But in fact, you still can, because they are, you can look at the structure. Actually, in the end, you'll find that the basic nodes is still the list nodes, is still the linked list, is still the linked list. So not surprising that if you really want to access the second nodes, third nodes, it's very hard for me to stop you to do so. But in theory, stack data structure, you're not supposed to do so. Okay, so this is something you need to take notes about the stack and cube. Of course, stack and cube, yeah, you also can implement it in array. Yeah, just linked list, I think is better because it's flexible. You can increase the size, decrease the size easily. But array, it just allow you to random access. Actually, for stack and cube, you are not allowed to random access the element. So probably linked list is still a better choice. Although I can use the array to realize it, but I think linked list is the better option. So okay, so that is this today lecture. For cover the next Tuesday lecture. Next Friday, I will talk more about this algebra expression conversion, which are going to use the stack data structure. You find that you have to use the data structure. I'm not worried you go and access the second element and third element. Because you want to do that, yeah, you only need the first element, the first nodes at the front. So you're going to use a stack to solve this particular algebra expression conversion, which actually is the algebra expression, how your calculator work. Yeah, why your calculator able to know they need to do the multiplication and division first. Yeah, when you place trying to do the calculation, why he know the order. Yeah, actually they are using this algebra expression conversion, yeah, to sort out the order. So in the lab, yeah, I will release soon the balance paradox problem. Also use the stack. Another thing you in practice, you'll find that actually if you have a recursive function, normally I can set that all the recursive function, you can convert it into the iterative function. And how to convert it? When you convert it, yeah, very likely especially the tough one, you need to introduce a stack data structure, because recursive function normally is implicitly they declare a stack data structure implicitly in the memory. Because every time you recursive call, they will push your function call into a stack memory, and then that stack memory is first in, last out. The first recursive function call will be the last return call in the stack memory. Yeah, so that's mean implied that recursive function actually they are implicitly build a stack data structure to store the information implicitly. So if you want to convert that particular function, recursive function, to an iterative function, very likely you need to explicitly declare a stack data structure to do this conversion to an iterative approach. Yeah. So for the queue, some classical problem is like palindrome to check whether the forward and backward, is it the same? Is symmetric or not? Yeah. Then in real world, a lot of scheduling algorithm are a kind of a queue. Are using the queue data structure for those system, multitasking system. Your router switch they're doing some network problem, network system. They're doing some scheduling, the job scheduling, mailbox, storage, all this. Inside, they definitely have some queue structure to store the package, store the task order, store the job order, and so on and so forth. Yeah, they are building a queue data structure to store the information. So I will talk about this algebra expression conversion next Friday. Okay? Any other question? If not, I wish you all happy Chinese New Year. Good night. I will go to the Zoom meeting to talk about the lab 1 question. Yes, probably, I don't know, maybe after Chinese New Year or before Chinese New Year. Let me see how this weekend. Okay? If no other question, I will go to open the Zoom meeting to discuss the lab question, this week lab question. If you're interested, you can join in. Okay? See you and happy Chinese New Year. Bye bye.